who is going to talk about overall algebras, entropy, and gravity.
Yeah.
Please.
All right. Yeah. So the title of this first lecture is Quantum Field Theory in Curved Space-Time. It's an approach to quantum gravity, which is basically a semi-classical approach where excitations of the geometry or of the matter fields are quantized. So in particular, the gravitational field around a background could be quantized, but it's a fundamentally semi-classical approach in that it's not the full path integral of quantum gravity, if you like, but it's just fluctuations. So you can treat it, you treat this theory, so it's also called semi-classical gravity. I don't like that so much, but it's just terminology. So you can think of that as an extension of quantum field theory to a setting where space-time is in Minkowski space, but some other Lorentzian space-time, such as an expanding universe, a black hole, or something like that. So before I get to entropy and quantum information, which does have interesting recent connections with the subject, I thought I was going to go very quickly through that. So I'm assuming you know we all had a course in quantum field theory, as in canonical quantization, field operators, creation and annihilation operators, possibly time order products, Wick's theorem, that kind of thing. Is that so? If any of those terms seem strange, maybe what I'm going to say will sound much more strange even. So let's start. So what's the difference then to Q of T? So by the way, this is a set of lecture notes which I prepared for another summer school like this a few years ago, maybe 3 years ago, also in Italy. So for this school, I've revised it and updated them, but it does not contain an introduction to quantum field theory in curved space-time, but to quantum information and QFT and algebraic QFT in particular, which is going to be the main subject. But, before I get spend a few words on quantum field theory in curved space-time. So what's the difference with the in flat space? Well, it's more complicated because waves on a black hole, if you look at them even classically, how they propagate, it's very complicated. But that's not really my point. Whether some things are technically more complicated or not is, after all, you can master it. But really, there is a difference of a conceptual nature, which I think is more difficult, though it's easy to say, but it's more difficult to really understand. And it's the fact that there is no preferred vacuum state, or in the algebraic approach that you were exposed to a little bit, you could say there is no vacuum representation of the algebra, but since the state is related to a representation by the GNS construction, it's sort of the same thing. And physically, that means a lot of things. So there is no notion of particle in general. In general, no S matrix. So saying all these things, and there are no space-time So, of course, when you learn quantum field theory, what you learn it for is to describe particles. That's what this was historically the motivation for, like electrons, positrons, photons. Later on, other particles associated with extensions of QED, but it's all about particles. But that's a historical thing. In quantum field theory proper, you eventually learn that what you have are fields, like the electric field, the magnetic field, the Dirac field, and those fields are quantum fields. And those fields may have states, and in flat space they have states which look like which have like a concentrated density of energy momentum propagating approximately along a straight path unless they collide, and that you are entitled to think of as particles. Now, in a curved space, there is no such thing, and the problem starts with even saying that you have a state with no particles, the vacuum. And why is that? So this is just pictures. So the standard argument is something like this. So now I'm also assuming that you know a little bit of general relativity. So if you have an expanding universe, like for example de Sitter space, such an expanding universe is characterized by something called expansion factor. And maybe you believe me for a minute that you can quantize a Klein-Gordon quantum field theory on such a background. Maybe say a few more words about that. And you could imagine maybe that here, down here in this slab, maybe the expansion is constant, some constant here, and maybe in this slab, the scale factor also is constant, maybe some other constant, and it evolves in between. Of course, if you have heard a class in general relativity, such a metric with a initially constant a scale factor, a universe which is static, then does something static again. It's nice to imagine that, but it cannot exist. It will have a stress tensor with a negative energy density, so it cannot exist. But let's think you did have something like that. Then while you're in epoch 1, you're just Minkowski space with some A here, which you can set to 1 by a change of coordinates. So you have quantum field theory here, and you have a vacuum state. But also up here, maybe many years later, you have again Minkowski space, and you have a vacuum. So you have a vacuum state maybe down here and a vacuum state up there. That's not a problem, but which one is the vacuum? Because you can easily convince yourself that they cannot be the same states, because if you would imagine if this was not a background gravitational field, but instead a background electromagnetic field, what you would of course get is that the changing background fields will induce the creation of particles. So these states are not the same. So in fact, in the good circumstances, you can write this as some constant C1 plus some constant. So schematically, so they're definitely not the same states, and you can this is a bit schematic. You can write these things, you can calculate it. So which one is the vacuum state? Of course, it's neither. They're both states, and for a particle collider built in this epoch of the universe, you would work with this vacuum state and its excitations. And in a later epoch of the universe, you would work with this state. And this state would secretly have in it, relative to this one, a lot of particles. But in practice, those would be particles with very soft momenta, so you would never measure them. But they were different. So there is no preferred vacuum state. So this is, of course, a highly idealized situation. As I told you, such a space-time can never exist. It does if you compute the Einstein tensor for this metric and set it equal to the energy momentum tensor, then such an energy momentum tensor will have very unphysical properties. And that, of course, corresponds to the fact that general relativity doesn't like static situations. It's an inherently unstable theory, and once something expands, it will expand more and not settle down. So there is no preferred vacuum state, and you can imagine if there isn't a preferred vacuum state, it can't be, like a particle is supposed to be an excitation of the vacuum state, so there is no excitation, there is no S matrix, again, and so forth. So that doesn't mean that people doing high energy physics have no sense. It just means that if you take a very global viewpoint of space-time, not a local one where the metric is nearly constant, then these things stop making sense. It doesn't mean that if you work locally, you are not allowed to work with a vacuum. It's just that the global thing isn't describable in terms of a vacuum. So if you don't have this, so the usual formulation of QFT built on this So for instance, if you write something like a field T and X is like a D and K. Omega K, and then we have a formula like this is, you see what the problem, so this A is obviously of the same class, so that's a formula from Minkowski space, which I assume you've seen at some level. So you may think that in a curved space, this is of course a solution to the Klein-Gordon equation here. So maybe and A of K on the vector is 0, so that kind of defines the annihilation operator. So you may perhaps think that what you need to do is to substitute another mode here. Yeah? So this is for as K runs through all the momenta. This is a kind of the basis of modes. So if we define U of K as T X. So then you may think that all that you need to do is a plane wave, obviously. Yeah, so it's a superposition of plane waves. So you may think that all you need to do is you define a new set of modes, complete set of modes. So what would it mean complete? So UK primed in something called Klein-Gordon in a product. It's basically not sure whether you know the Klein-Gordon inner product is something that regularly comes up. Quantize a field, UK, star, and then GT left, right. That's called the Klein-Gordon inner product. So it's easy to guess what that would be in a general curved space-time. So why cannot you do that? The problem is it's the plane waves. There are plenty of modes, but why not take cylindrical waves in flat space-time or spherical waves? Yeah? So you can build an orthonormal system of spherical waves or cylindrical waves or waves emitted by an antenna of some shape. Why not that? Well, the reason is if you do that, then what you no longer have is a representation of the Poincare, a reasonable representation, yeah, because the waves that are emitted from an antenna of some weird shape, they don't transform nicely under Lorentz transformations. And it's secretly that's what's behind picking this particular basis of mode function. So this is a basis-dependent function. So the problem here is the choice of basis of mode function. There's no orthonormal basis of so UK, so K after all is just a label. So how about some other formula that you will have seen in quantum field theory? So many people like the path integral. I like it too. So why not just use the path integral? So you may be worried that how to define it, but surely you could say maybe the vacuum maybe you want to define it like this, so you define it again to some proportionality. This is, I assume, is a formula you will have seen. Okay, so this is a path integral. So d of phi is the formally product. So okay, it's not easy to define this, but I'm not claiming this is a technical problem here, but I'm claiming it's a fundamental problem. And the problem is really you're in the curved space-time, you would again define this by making a choice of basis. And then defining the path integral measure with respect to this basis. So the problem is there isn't the d phi doesn't it's not unique. Yeah? So if you think about it, what it really is, then you will realize it's just not unique. Yeah? So it's only unique if you say in flat space that it's invariant under translations and Lorentz transformations, then it's okay. But if you don't have that selection process, you just cannot define it unique. So this is not unique. It's not defined, and that's the basic problem. And if when you try to define it, really, you start having to make some choices. Okay, so that doesn't work either. So really, this is normally even time-ordered product. I left this under the rug, but it's not a problem of the time ordering or not the time ordering. It's a general problem. So the S matrix, again, S matrix is a great thing, and it would make sense here, where you have some incoming particles. After all, this is basically flat space. And you have some outgoing particles. So you can define the S matrix by taking appropriate inner products between ingoing and outgoing states. But what if you have a space-time that never becomes flat in the past, like our universe? Our universe was never flat. It just becomes more and more curved as you go back to the past. So you can see from that everything. Matrix. So this not unique, so now it doesn't. Okay, so but you do want states. We don't want to change the rules for quantum mechanics or quantum theory. So what do you do? So we just have to avoid thinking that there is a globally defined reference state for everything. That's maybe a postmodern viewpoint. There aren't any really undisputable reference points for anything. You just have to accept it. And so the language is algebraic approach. So what would that be? So the algebraic approach is nice. It's just a language in the end, but it's nice, in my opinion, because you can somewhat disentangle things that depend on choices, like certain states, and things that do not depend on choices. And so what doesn't depend on choices are the algebras. So they depend on the dynamics of the quantum field theory. Let's say just, if you like, the Lagrangian and on the metric. But otherwise, no choices. And then there are the quantum states. They depend on the physical situation that you want to describe. So you have to be, just be more careful what you mean, what the situation is that you want to describe. You cannot just say, I want to describe a two-particle state. You don't know relative to what. But if you say, I want to describe a state in this or that space-time, which is in thermal equilibrium, etc. So the more precisely, axioms that you use are quite similar to Minkowski space-time. Now, so you have basically for every so before as you recall, you say the algebraic approach is that you say you have an algebra for every region of Minkowski space, or if you're a bit more careful, you say you have one for every causally complete region. So here you just say you have an algebra for every globally hyperbolic space-time. So you may think that this is somewhat less. What if you have a region of Minkowski space? Well, the idea is simply that if you have a region that is, let's say, in Minkowski space, a causally complete region like a diamond, then you take the viewpoint of general relativity, where you say this O, and in this case the flat space-time metric, you regard this space-time its own yeah, so that somehow seems a trivial change, but it's the viewpoint of general relativity. The space-time is not just the metric, but the region, like the manifold and the metric. And so Rindler space, for example, which is the wedge for study general relativity, that's a space-time that's different from Minkowski space. Because, for example, has incomplete geophysics that leave the wedge. So it's a different space. So this is included as a separate space-time. Now, the key so star algebra here, it's C-star algebra, for example. If you don't want to be too specific, you need the star always because you want to know what's Hermitian. So you know quantum mechanics about Hermitian operators. That's why you need star. And there's some other important idea. So before in Minkowski space, you want the key thing you want is the local commutativity. So if you have two diamonds and two observables in space-like related diamonds, they commute. So the way you set it up here is a bit different. Of course, you could say that suppose you have two regions in the space-time and they're space-like, then the observables commute. You could do that, but there is a better viewpoint and a more fundamental viewpoint that I'll try to explain, and that's the following idea, which I illustrate in a picture. So let's imagine you have something like here, you have a space-time mg, which let's say mg, m is two dimensions, so it's a time direction minus times a circle, and the metric is this, where x is identified with x plus I. So that's a space-time. And here, let's say you have some other space-time with just a little diamond in flat space. So this space is also flat. It looks like it's curved, but the metric is flat. The Riemann tensor is 0. It's also a flat space. It's just a flat space with identification. Identification doesn't change the curvature. So you can imagine you have something that is an embedding. So you have a piece of flat space, causally completed, embedded in here. So you kind of want to say that if you figured out your quantum field theory in this region, then you kind of figured out the part of the quantum field theory in that bigger space-time restricted to the small region. And it sounds almost trivial, but so let's imagine you have some map here, and so then the condition that that these metrics should be compatible. That's in GR language is written like this. Yeah, so it says that this split piece is really a piece of this space-time and is causally complete. So there are no curves in the larger space-time. No causal curves that connect to points in here that somehow leave this region. Yeah? So that you must have. And then you want to say that there is some alpha chi going from so this is the smaller algebra, and this one is the larger one. You want to say that this is inside this one. So inside, or it has the same relations. So it means for algebras, it means that this is a homomorphism. Yeah? Homomorphism is something that preserves the product. And in fact, since we always have a star, it should also be a star. Yeah? So this should be a star homomorphism. So we require that we have that. And in fact, if you iterate this, so now maybe you could imagine that this one was maybe only going to up to some time here. And then in the next step, you allow the time to be from minus infinity to plus infinity. So you would have another such embedding. So then you would ask that that it's compatible. So this is sometimes if you have heard about some very abstract mathematics called a category theory, and there is something called a functor. Yeah, so there is in the category arrows, and the arrows at the classical levels are the embeddings, and the isometries, so the causality preserving embeddings, and the arrows on the algebras are the star homomorphism. Yeah? So it's supposed to be a correspondence. So let's see how this gets us to space-like commutativity. Maybe that's not totally obvious. So you can do something that looks silly. So let's take M and E to be, I'm drawing just a picture. So it's the disjoint union of two diamonds. So disjoint union means just that, do I have to explain what the disjoint union means? Just have nothing to do with each other. Yeah. So the two spaces are just a disconnected set. So usually we think that a space-time surely should be connected because if I should be able to go anywhere, but maybe it's not. So that's a space-time. And now let's embed that into a larger diamond. So one here, let's say the other one here. That's my chi. So this could even be flat space-time. Everything could be flat space-time. So this is a causality preserving if I don't create new causal curves. So the fact that I don't create new causal curves means that these have to be space-like, separate. So this is causality preserving. if the image of the space-time space-like, causal. And so this is the whole thing is then my M tilde, just call it. G is kind of boring. G is always flat space-time. So why is this now gives me an interesting relation? So in this algebra here is just it's just going to be the tensor product between the algebra here and there. There are no relations. They're just different space-time. No relations. So therefore, in particular, since the factors in the tensor product are new, these observables from here, they must also commute. Space-time commutativity is a consequence. Of this okay. So maybe you've heard about, maybe in more concrete terms, if you've taken a class in quantum field theory or conformal field theory, sometimes people talk about S matrices, sometimes people talk about path integrals, sometimes people talk about canonical quantization. So but there is another viewpoint that's sometimes taken. It's called the operator expansion or operator product expansion. Have you heard about that? So this kind of axiom has, I think, is a kind of a more global thing than the operator product expansion, but it does have maybe if that's too abstract, if there is an interpretation or a consequence really for the OPE. So what's the OPE? The OPE is the statement that there are somehow operators in the theory and then there is a statement about that somehow this you can expand this I'm not going to go into what really this similar sign means, but it usually means that it's not a really convergent series, but it's supposed to be a good approximation for short distances, or at least on the light cone or something like that. Now, if you think about this situation here, what the axiom would say. So the operator product expansion is like the algebra. So these are like the structure constants of the algebra, right? And this instruction or this axioms or whatever is telling you that the image, the algebra here is just the image of that one. So the relations are exactly the same. So what it means in terms of the OPE is that the OPE coefficients here and the OPE coefficients that you would compute in this manifold and in this cylinder, that up to this identification, they're exactly the same. And so if you compute the OPE, even though you have periodically identified deals coefficients in, for example, these coordinates are not just approximately the same, they're exactly the same. The local physics does not care about global identification. So this is the condition on the OPE coefficients. You can think of this as a consequence. So if you think of them as depending on the space-time manifold, then they always obey a relationship like this. So there is another axiom in ordinary Minkowski algebraic quantum field theory, which is the axiom of covariance under Poincare transformation. So I'm claiming that also already is included. So if you think of a Lorentz transformation, so a Lorentz transformation you can think of as an isometry, right? Linear transformation, obviously, you know that. So normally you say it's a matrix, and it's a boost or rotation or whatever. But from viewpoint of general relativity, it's an isometry of Minkowski space in the sense that G is now Minkowski space. The R way to say that the Lorentz transformation preserves the line element, yeah, so the R version of it. And now, of course, the Lorentz transformation being an isometry, you can apply this in an even better situation, because G is equal to G tilde. So whereas this is just covariant, it relates something different. If you have an isometry, you get this alpha goes from the same algebra to itself. So you get an actual condition, one algebra, and not a relationship between two. So you get to learn that alpha I, it goes from AMG to itself, and that's the star. It preserves the star and it preserves the product. So that's covariance. Yeah. So you have some transformation preserving the star and the product, and obviously it is this second axiom here, and is telling you it preserves the product of Lorentz. So it's a kind of trivial and a kind of a really interesting at the same time. So it's trivial in that just arrows and words, but it's kind of expresses something very non-trivial if once you go to an example. And so that so I said I was going to do 45 minutes and break, and I think that would be the point to break here.
Are there some questions on this first part?
You can ask me privately.
Okay. So, we have a short break and then we will see.
Maybe 5 minutes?
5 minutes.
5 minutes.
Okay.
Ok, tu avrei votato per 7? Non la penso che va bene, perché ha detto di sì. Dovremmo essere a posto. A me l'ha mandato, ma non
Io stavo chiedendo come non ce l'ho seguito. Sulla pagina.
Eccolo. Forse è arrivato qualcosa? Sì, è arrivato adesso, ok.
So did you like the concert yesterday? Okay, maybe you will say it doesn't. Yes, yeah, it was okay. It's more patch.
In the second axiom,
Yes,
start saying that I remember that then it can be explained next to this point. That means that asymmetric means give you some examples. It's different from a symmetry. Symmetry,
e questo chiaramente però diciamo le situazioni
different from
è solo una reequilibrazione, ma adesso
how things are identified.
si riesce a fare. Quindi è più o meno la stessa cosa.
I'll say a bit more about that. In a sense that you unify the two things. Yeah. So it's not as if you want to see
Tutto rassi.
yeah, there does not express can express symmetry.
Almeno gli stati asintotici. Sì, certo.
Non è che non si può.
Sì, sì. Yes, it's upstairs. You want no, it's not so far. If you want, I can tell you. Yes. I can show you.
I mean, just get my money.
Yes.
No.
There are other people here that will be. He's like establishing his mind in 20 years, so he's way so good.
Mi dispiace.
Ma che così poco. No, ma tanto io passo da sotto.
Però da sotto io che non ci passi.
Vabbè, ma io sono relativamente bassa. Non sono ah, vedi? Questa è un po' la no, facciamo due passi fuori, siamo andati avanti.
Ma hai visto il personaggio così
Sì, sì, certo. Sì, sì. No, chiaro, ci sono capito. No, devo dire che non è che abbiamo tantissime cose, oddio, non so che cosa dire dopo. Siamo andati lo so, la mozione di macchina poi di no, infatti io c'è stato in parallelo però vabbè, c'è stato prima qua di cui non fare nel senso che dobbiamo fare e vabbè però non mi c'è ah, dici che no, comunque mi avevano detto che poi c'era
sì, no, vabbè, se vai
non so se sia
se adesso questa
Per quello poi non siamo mai andati. Sì, no, ma anche perché magari lasciamo perdere il banco, sì, siamo d'accordo, no? Però pure se vai sul diavolo figo, no? Un po' più avanti dove c'è stata la connessione pure su una
ah sì,
comunque questa è la dimensione, sei uno sopra l'altro, quindi
devi fare la scalata dopo le gallerie.
sì, no, davvero.
Vai giù,
Andata.
vai giù così e bello perché c'è la finestra.
Ah, ci siamo andati a queste tabelliere a Pescara. No, ma sai, se non ho capito io, ci siamo andati una volta, siamo arrivati a questa tabelliere a Pescara, stavamo tutti messi così sotto al bar, e abbiamo, per quello non mi ricordavo. No, ma poi
devi
sai
andare
ah, stasera sono andata a questa con un'amica mia a Facaglia, no, è vero, però pure lì non è che c'è questo spazio.
no, però è un po' di
Vabbè, sai che c'è quel fatto che lui, cioè, non è che lo fa apposta, ma proprio non l'ha fatto. Tante volte se andiamo al mare ce l'ho cannacci di pure per 5, per me nel senso, no? Ma io ero una delle prime che si piazzava così, mo lo so che non si direbbe dalla mia carta. Sì, sto parlando pure nel senso che hanno comunque sono bianche, ma hanno un po' più decolorito, io sono quasi verdi, certe volte ce l'ho avuto. Quindi non mi chiedi che
okay, so
Okay, I continue
We start,
here. So I want to continue with this. So there was a question, but I like that there were some questions in the meantime. I think you don't have to get through a particular curriculum, so I'd much rather answer your question. So one question from you was, what's the problem with the path integral? So let's do the path integral again. So what would you do normally? So we don't normally like the I in the path integral. So normally you say you get rid of that by something called a Wick rotation. Where you say that T I tau, that's a triviality, the definition, but then you say that this thing has a sufficient amount of analyticity, so you can actually do let tau be imaginary. So go to a contour where tau is real. And so we normally I used to say then that this is, let me put a bar here for the rotated thing. And then I get here the so-called Euclidean action. As you know, the action, let's say for a Klein-Gordon field, would be kinetic minus a potential. Like this, the term. So of course, to put a t to I tau, it formally changes this sign here. This is my sign convention is the other way around, but the Euclidean one would be where there is a plus. And then you would say this is a Gaussian integral. So a Gaussian integral is kind of the inverse of this differential operator. So this would be a minus this integral here. And so you would normally say that this is then 1/2. And that's there's no problem with taking the inverse of an operator. So the difficult, and this is okay if the Wick rotation works. So if you here in Minkowski space, it works because you go from Minkowski space to Euclidean space, and from Schwarzschild you go from Schwarzschild to Euclidean Schwarzschild, which is a nice Riemannian manifold if you identify T-tau periodically in an appropriate way. But in general, a Lorentzian manifold, you just get garbage if you get some complex metric. If you can analytically continue the Lorentzian metric in the first place, general solution is just as smooth, so that's not even analytics. It's not a question about this procedure, but the question is about the generality under which this procedure works. And it gives a state, if it works, and for example, in Schwarzschild, it gives the Hartle-Hawking state. But in general space-time, it's just not applicable. That was one question. I'm very grateful to it. I said these things more clearly. So it also indicates I don't have opposition against this procedure. It's just that the question is about the generality. It's about conceptually how general is this, and can this be used as a real general definition of quantum field theory? That. Now I wanted to go down my list. Covariance of quantum field. So a quantum field is local, so it means that on a fixed space-time, my quantum fields I'm going to call O here. It's actually occupied on space-like. So this kind of thing is already included in my axioms because I usually say that O is really a distribution. So I should do something like this. So let's say the support is a diamond, and let's say the support of prime. Prime is no different derivative. Anything is in a space-like related time, and then what that means is and it's already ensured by saying that P of F is in the algebra, this INN here, and the other guy is in a space-like related diamond, and we already know that the algebras can. So this is okay already, but there is another kind of covariance which normally would state that state in the following way: if I apply a Lorentz transformation or a Poincare transformation to the argument, then that means the operator is conjugated by an appropriate unitary operator. So the normal meaning Minkowski space, a normal condition or property is that, for instance, if you apply a Lorentz transformation, suppose you get a unitary operator here. Something like this, and similarly for translation. And in curved space, it's not difficult to imagine we should have that in general. So there is just no Lorentz transformation.
There's O inside. Oh, yeah.
So we're looking for kind of a replacement of this. So it's clear that they can't be a replacement because the curved space-time, it's just an illusion that there have symmetries. It just happens that it's more like we can only find solutions to the Einstein equations which have symmetries because the other ones are too complicated to write down. And it's much more like a space-time is not like a perfect sphere, but a potato. And a potato does not have a symmetry, and it doesn't make any sense to require that something should be transformed in some way if you rotate the potato in some way. Yeah, it's just has no symmetry. But there is something still that's a bit harder to grasp, and it again has to do with the fact that space-times can non-trivially be part of larger space-times. So I had this picture before. And so there is an embedding, and hence there is some identification between the algebras. G. So we agreed that there was something. So I would also like to say more precisely that if I take a quantum field localized at this point and I push it forward, I get precisely a quantum field there. So what I should really say is that if I have a quantum field that I construct on the larger space-time, and I apply I get evaluated at the image of some point x, then this should be exactly the same as taking the quantum field, bringing it over there. So this kind of a formula. You would like to postulate. Now, I think the difficulty is not grasping such formula, but the difficulty is understanding why they tell you something non-trivial. And so I'm going to try to explain what this means in an example. And to formulate the example, obviously, I would have to start setting things up and how you quantize a free Bose field in curved space-time and so forth. But let me imagine I really deal with this shall I explain it now? So let me say here that this gives a non-trivial description of how we normalize but if I want to, I would have liked to give you a concrete example, but I think I still need to explain a bit more how you deal with these free fields. But just to give you the idea. So let's suppose you deal with a free scalar field. So the free scalar field, you can represent it as an operator on the vacuum, in the vacuum representation. So this would be K, to ignoring pi's. So that will be the free scalar field in Minkowski space. Now, how would you think of the free scalar field so in particular on this patch? So how would you think of the free scalar field in this so-called Einstein cylinder? So now it's quite clear that you're going to have not a continuous set of modes, but a discrete set of modes, because you have to enforce a boundary condition that the field is periodic, and if you put an arbitrary momentum, it's not going to be periodic. So the field in this in the Einstein static universe is going to be, if you prefer to write it as like K as n infinity, and then you have one over K, and X is conjugate, but the condition is, let's see that K is 5. And so it's a discrete sum, so you will not be very shocked. But how are you going to see that this is the same as that? Yeah? So you have to understand really that this lives on a different Hilbert space. It's realized on a Hilbert space built on the ground state of this space-time, with the modes having discrete set of frequencies. So you have to, so this alpha, this embedding, will involve So this other is between abstract algebra. So if you have a concrete algebra on a Hilbert space, it must also involve the identification of the Hilbert spaces, and it has to do it in such a way that this formula becomes exactly this formula. Yeah, so this is not totally obvious that this. So how this is to be done.
There's some operators.
Yeah, I guess so. Yeah. So it's a tilde here, so a different equation operator can keep it on a different Hilbert space. So you see this alpha has to incorporate this precisely. So now let's do something even more interesting. So this you will believe me that this is somehow done. I mean, it's just okay, but let's suppose I want the operator, which is supposed to be the square of the field, sometimes called the vacuum polarization. So this, you should think that this flat space will be defined, saying that this is again up to some pi's. So 2D, I guess I have the logarithm. This would be the operator coefficient of 1. Then would be the field phi squared with the operator coefficient of 1. So that's how this field is defined. So normally you would be used to say that how I get this is by normal ordering it. So I take the naive square here of this, so it's a double integral. And then that's not great. That would not be this field that appears in the OPE, but the one that appears is the one where you apply a weak ordering, meaning that you put all the annihilation operators to the right. So this would be the formula in 1 plus 1b. Other terms. Now, so let's take as the view. So let's define let's say phi squared and be as really the normal ordered squared. And let's say you do the same on the Einstein static universe, where again you think that maybe you should just normal order this. So this has also an expansion in creation and annihilation operators, so you can normal order it. So I'm claiming that this would not be a legal definition. It will not satisfy this. And the way to see this is that when you normal order, really you're taking away the singular part. And the singular part depends on how you write the fields in modes, because it's a 2-point function you get from the mode. And so there, if you do it like this, there is a choice, an implicit choice of modes made here for this. And that space-time and an implicit choice of modes is something more. Yeah, it's something that you, some additional thing that you secretly assume to have, and it's not. So this is closely connected to the Casimir effect, because the true phi squared, which does satisfy this, and which is not the normal ordered one, because it's not the normal ordered one, the normal ordered one has a vanishing expectation value in the ground state being the one we're annihilating by A. But the true phi squared, which is the one that satisfies the axiom, that does not is not the normal ordered one, and so therefore it has a non-zero expectation value in the ground state. That's called the Casimir energy. And the Casimir energy is something that's measurable, and it's measured to be non-zero. It's not measured for the vacuum polarization, but for the energy density, but it's a mathematically analogous problem. So in a way, it's not just a mathematical prettiness, but it's really you get a physically wrong result. Yeah? So you have to renormalize, even if you're, maybe say differently, even if you're on this cylinder, you have to renormalize, of course, the vacuum, the ground state knows that there is an identification because the modes know about the identification. But when you renormalize, you must not know about the identification. You must pretend you're in this, you only know this piece, you're in this piece of time. So this is an enhancement of locality, and this is there, in this sense, a renormalization, a way to renormalize. It gives a constraint, or it tells you how to renormalize. Okay, so this was the general story. Now, I wanted to say a bit more concretely what kind of states, popular states that we have for manifolds, and I mean the ones that are of main physical interest in general relativity. So this would be the Laplace space actually. But because I've been a bit sketchy, maybe let me then state how to quantize at least the Friedland-Gordon field in this setting. So let me again say, so the Friedland-Gordon field it should give you, so the normal viewpoint is that it's some sort of operator. X. So it should satisfy this, and it should, it's normal if we say it's a real field and permission. And then usually we, for example, perform canonical quantization, and if we set it up like this, so we would then demand that it fits some time and make the space-time split. So this would be I. That would be independently of t, and this would be considered as a canonically conjugate momentum. I assume that your Q of t class would have had dealt with canonical quantization, or alternatively, we write a formula that we've written a few times, but we could write it in sort of a more general way. this is the Minkowski space. So what do we do? So first of all, every quantum field theory book writes this Q phi of x, always, so phi t and x. But, and all the problems, why everything is just so many things are just formal, is because you don't acknowledge that this is not a function, but it's a distribution. It's a very irregular thing. It's a distribution valued in operators. And there are some things you can do with distributions and others you cannot. And so the first step to be a bit more precise would be to acknowledge that it's a distribution. The others, however, have already done this. So let me not, for the moment, emphasize this too much, but let me say how you get an algebra for this. So we just introduce, since this is a distribution is just something that's lying in the bush and it's waiting for a test function. And when it sees the test function, it averages. So I'm using this notation. Some people find it confusing. It's just the average. And so the algebra for some mg, so the fine print is that this should be the so-called globally hyperbolic. Explain that. Second, so you just say, so the nice thing about distributions, the distributions are of course generally more complicated than smooth functions because they have singularity. But the nice thing is you can always, in calculus, among the first things that you learn is that you have to be careful when you take derivatives because not every function does a derivative. But the great thing of distribution is because it's such a general thing, it always has a derivative, always. And the derivative is it's a kind of a definition like this. So you say, what's the, in particular, we'd like, of course, this derivative here. We say we apply the derivative just to the test function. And then we imagine that if this was an actual integral, we would do an integration by parts. But because nobody says there's any meaning to this in the first place, it's just this condition. All test functions. So the term test function means a smooth function which is zero outside some sufficiently large set. Yeah. Okay. That was easy. And the second one is just as easy. So you, of course, want to take the star of the thing with the test function. And the test function just gets conjugated. So complex conjugation. That's also trivial. So the interesting, last interesting one is this. But maybe at first we should somehow express that phi of f is an integral. Now, it isn't an integral because it's a distribution, and a distribution doesn't really have an integral. It has something that formally behaves like an integral, and that's expressed simply by a kind of linearity. So you take as the feature of the integral that you want to preserve that it's linear. So that corresponds to this. And then the last one is this one. So in general relativity, you do not like a space-time split, or whether you like it or not is maybe a silly thing, but you don't regard that as, or in relativity, you don't regard that as having any kind of particular meaning. And so a better way to rewrite this is to say that this is I times, and now I really have an integral. And I have to tell you what is E. E is the advanced Green's function minus the retarded Green's function. So what's the advanced Green's function? The advanced Green's function retarded. This is delta function, and we read is equal to 0. X prime is not in the causal path. So in other words, it's non-zero unless X prime is in the path shadow. This is a notation from general relativity. It means the causal path. Okay. So this is called the retarded Green's function. The advanced Green's function is defined by just changing the path to the future. This is called sometimes called the causal Green's, the causal propagator. So the causes, so the E satisfies because both are inhomogeneous solutions with the delta function cos. This is the solution to the homogeneous. It's sometimes called the causal propagator. Now, one thing about the causal propagator is that E of X is 0 if X is space-like to X prime, and that just simply follows because in such a case, the advanced and retarded propagators are 0 separately. So only non-zero, one point is in the causal shadow of the other. And so this gives you Einstein causality. I'm writing it in this kind of informal distribution way. So these are then the relations. The only thing you need to understand is, let's say in flat space, why you can write this condition as this condition. Call this star. The equivalence of star and 2 star follows from the simple lemma about these Green's functions. Namely, if you take the matrix E Tx at equal times. So where you imagine that you you split somehow arbitrarily space-time into a time piece and a spatial piece. So you can do that in what is called a globally hyperbolic space-time. And then with respect to such a split, you can then talk about equal time commutator. And then if you look at this matrix here, this matrix is precisely given by I times this Bloch's diagonal matrix where you have here the spatial. So this may be a little exercise. You can work out why this kind of a condition implies equivalence of this and that. Okay, so this is how you can define algebra. So I think I've explained where these relations come from. So now the algebra of MG, this example, it's just the algebra generated by identity phi of f and by kind of symbols that should be as functions. So it's a free algebra, meaning that there are no relations. Yes, it's like these are letters, and then you should build from them words. Yeah? Called free algebra, and then you divide out this kind of relation. You can always divide an algebra, a free algebra, by a set of relations. That's the definition. So you can just define something. There is no Hilbert space here in this game yet because there is no mentioning of Hilbert space. There is no mentioning of creation operators. There's no mentioning of path integrals or anything. So you should, this is a pretty trivial thing to do in a way, but you should be under no illusion as to how complicated these advanced and retarded propagators are on a curved spacetime. So for example, in Schwarzschild spacetime, which is algebraically certainly not a particularly complicated metric, you can write it down, probably you can easily write it down. Nobody has an explicit formula for this. So if you have one tomorrow in terms of some special function, non-special function, I mean, not one that defines this propagator, but that's known before. Let's say Euler, or you would be a very, very famous, very difficult problem. Yeah. So this is, of course, is an illusion to think that this is really simple. It's just all the complicated behavior, even for this free field, is hidden in the propagation of classical waves. Yeah, that's very, very complicated in the curved space. Now, that is the algebra. And then, just as in general, just as usual, I will write QFT, as my other colleagues have explained or will explain, states are at first expectation value in ordinary quantum mechanics, we are used to write the expectation value of A and or general mixed state, usually meant to be trace of rho A. This is the expectation value functional. In this case, it's in one-to-one correspondence with the density matrix. So this that makes perfect sense if your observables are already on a Hilbert space, but here you have an abstract algebra that is a priori not on a Hilbert space. So a state is defined by linearity and positivity. Did you exclude Roberto, and did you already explain this? Yes. So I will not go into it. So since I would like to emphasize here that example, and then this gives rise to by the G and S construction. And this gives a representation of this algebra on the Hilbert space of this defined by the state. So again, as in flat space, the Hilbert space is coming through the back door. They're not on the front page, but of course, eventually we want them. Up to a point, it's a matter of taste. Yeah? So you can do one or the other. After many years, I didn't initially learn it this way myself, but what I appreciated after many years is that it's this way, this algebraic way, is better if you have a situation where you have inequivalent representation. So I mentioned before the space-time, which is initially static and then expands and then is static again. So I could do this construction and I would have, for example, two states. One would be the in state and the other one would be the out state. That's all nice. The issue is that the Hilbert space representations would not be unitarily equivalent. So unitarily equivalent means you explain, sorry, what is unitarily? So, yeah, so if you have a sufficient amount of, if the expansion is sufficiently rapid, then you create so many particles in a way that the in Hilbert space, the in vacuum would be infinitely crowded with particles from the point of view of the out vacuum. Infinitely crowded is the point. So they're really disjoint representations, and in my head, it's just silly to define the theory in one or the other when really they're both just two representations of the same thing. And I think that's why this viewpoint in general is superior. Okay, so let me mention a few states and examples before going home. So, how do I define a state from a pragmatic viewpoint? theory. Well, from a pragmatic viewpoint, it's what you're used to, I would say. So for pure states, one approach is modes. So I've already mentioned that, and now I'm mentioning it again. So a mode is just a solution to the Klein-Gordon equation. I'm going to call U, and lambda is the mode label. So the mode label would be discrete. If the spatial slice is compact, and it would be typically continuous if the space-like slice is non-compact. But it can also be a mix, so it really has to do with properties of the space-time. So I don't want to specify what the label is. The label is just from some labeling set X. And the connection between what you need is that the Klein-Gordon inner product delta function. So the Klein-Gordon inner product is what I defined before, except that I now do it in a slightly more general way. So U lambda A element. So this delta function is defined with respect to measure. So and even more, so if you have a space-time which is, let's say, of this so-called ultrastatic form, so then this part here is a Riemannian metric, which would have a Laplace operator here, and one choice. And this operator, let's say, would have a spectrum. So this lambda is the spectrum of this operator. It would therefore be like a momentum. And the and U lambda, so if the eigenfunctions if this is something like C lambda, then the mode would be X, so it's the same formula up to some so this IT X and omega lambda squared is the eigenvalue plus operator. So, sorry, this labels the spectrum as a label. So there might be multiplicities. Yeah? So if you have a symmetry like a Schwarzschild, then you get a lot of multiplicity. So you need a different. You cannot just take the eigenvalues as the labels. So this then you can then get a kind of a representation of this algebra from such a mode sum. So this is just the ordinary lambda here, and then times the node function. And some a lambda. So it's the same formula. The only difference is in the interpretation. The interpretation is that each mode label gives a representation. Yeah? And not the quantum field is what it is. It's in the algebra, give modes, just give a representation. It's very useful if you have mode sets that define inequivalent representations for the Hilbert space. So this defines representation. And G. So this is one way to get a state. So you have to pragmatically solve the wave equation or the Klein-Gordon equation. That's difficult enough. And then you have to Klein-Gordon normalize. So if you do that in Schwarzschild, you take this equation or you find the not quite. It's slightly more complicated because you have a non-trivial lapse function, but basically you solve the eigenvalue equation by separation of variables, like the Schrödinger equation for the hydrogen atom, and you're left with a radial equation called the Heun equation that Guido and you guys know a lot about. So just solving the equation for one mode is very, very complicated if you accept that a Heun function is a complicated thing. And now for the quantum field, you'd have to do the sum over all Heun functions. So that, of course, nobody can do, but if you could do it, then the vacuum state in this representation defines our modes. So now I'm writing it out in a completely kind of invariant way. So this is in the algebra, this is in the operator in the Hilbert space. This has a formula in terms of modes. So if you want to know this so-called two-point function, what a theoretical physicist would just call like this, reduce a notation, or they would call it G. Yeah. You have to understand there is a choice here. So even in Schwarzschild, there are different choices.
Sorry, which boundary conditions you choose to solve the?
That's exactly right. I'm coming to this. So even if you do it like this, as you know, notice right away, if I say I solve the eigenvalue equation, I have to tell you what kind of a boundary condition I'm going to put. And so if you put different boundary conditions, even if you have a field in a box, you could put Dirichlet or Neumann condition or Robin condition, you're going to get a different state. So likewise, you're going to get a different state here. So the most natural state.
Sorry.
Yeah.
Also, the measure is your choice, or it's canonical?
No, the measure is canonical because it's really what you mean by the delta function depends on the measure. Yeah, but so this is just a general procedure. One possible one. Another one is you go by analytic continuation, and that's essentially the same method, different guys, but it's applicable to the same class of spacetimes. And so it's defined by analytic continuation. So here it's different. It looks different, but it's the same. So first of all, the class of states, spacetimes this applies to is more or less the same. I'm just slightly restricting myself here. You could put a lapse function here. It doesn't depend on t, that charges. That's about it. So you can observe that if you say that t is I tau, and you demand that tau is real, then you get a Euclidean or a Riemannian metric. And so more precisely, this is a metric really on a complex manifold, and the complex manifold has different real submanifolds. That's the right viewpoint, but never mind. So here, d tau squared plus I j. Okay, now you then get the Laplacian for this Riemannian manifold, and so you can, for example, take you can say that t is in R, or you could say that t is in a circle. It is the same metric still, but in the second case there is an identification. So again, what I mean by the Laplacian is it is to be taken what kind of a boundary conditions I'm imposing. So here I'm imposing a periodic boundary condition. So this is the Laplacian metric, or this Riemannian metric. The boundary condition stood. And then I can, if this spatial part, this is a metric on the spatial part. Now, the spatial part could still be a very nasty metric, but if it has some nice asymptotics, then this Laplacian will be a self-adjoint operator. If it doesn't have nice asymptotics, then over and on top of this, what I require for tau, I have to have possible different boundary conditions for here. So the systematic way of dealing with this is called self-adjoint extensions of operators. This is not usually done in quantum mechanics because it's usually obvious what the boundary conditions are. But let's say if you have IDS space, then it's no longer obvious what all the right choices are. And so you have to have a systematic approach, but this is too technical for this lecture anyway. So with so this would be the Green's function with my signature convention. This gives a unique Green's function. Under given boundary conditions, and so for it, since so you could have, for instance, this on tau, but also on x, so you could indicate it by t beta. Now, if you do the analytic continuation backwards, so then you get a Green's function, and I'm going to call W beta, and now on my Lorentzian manifold, which is a distribution regime. And analytic continuation backwards is a bit tricky because you have to say how. So if you have just an ordinary real function, it's under a continuous function, or smooth or whatever, it's quite clear what you mean by analytic continuation. But if what you're analytically continuing is a distribution, it's not clear, because the distribution isn't analytic in most places, or it has places where it just isn't analytic, so it's not clear what you mean by analytic continuation if the thing itself isn't analytic. So there's a whole mathematics behind it, which I'm going to skip, but then this W, once you have it, and then this defines a state functional on at least a product of true pi's. And so I'm going to write it with 2. And you can also get something on n factors. This would be, we would define, so this defines that. So this would define that by the rule of Gaussian integration or non-commutative Gaussian integration or whatever. So this would be 0 if n is odd, and if n is even, it would be a sum even, and the pi is over the shuffle permutations with the shuffles. Particular subset of permutation, which you know from Wick's theorem. I don't explain it. So this is the way to define a state by saying what the endpoint functions are as you want. So this is the first thing is really the interesting part, and the other one is sort of Wick's theorem. And it turns out that by this procedure, you again define a state. So this functional satisfies, obeys all the relations that there are in this algebra. And this beta has the interpretation of an inverse temperature, because it turns out that the state with regard to the translations of this time is a KMS state as just defined before. So this is not a pure state, but it's a mixed state, a non-pure state. If beta is infinity, and if beta is infinity, then this construction is equivalent to the one I was explaining before. This is very similar to other spacetimes. Now, those are just choices. So you may ask, so what if metric isn't of this form? So how do I find a state? So the answer is you have to say what physically you want to represent. Yeah. So that's the thing that's not emphasized in the QFT books, because in flat space it's evident usually that what you want to represent are n-particle excitations of the vacuum, and that's taken for granted that that's what you want to represent, and so then you build up a machine. But if you want to in curved space, quantum state represents something very different in particles in empty space. You have to ask what you want to represent. So this represents a thermal bath, or the other one represents a ground state. But there are also other states in rotating space-times that represent not a thermal bath, but really, in a way, a steady state. So something like something represents a constant heat flow between thermal baths at different temperature. So there are the analytic difficulties are in defining the states. That's done by solving PDEs. That's what you have to do. And you have to get smart about. Now, in my next lectures, I will move on to quantum information, but I will give you a few more states in black hole spacetimes, but more like by drawing Penrose diagrams rather than explaining in detail how they're defined. But if you want to become an expert, you have to join the gentleman here and learn how you solve the radial equation in Schwarzschild spacetime, spacetime, and start calculating. It's very difficult. Okay, that's what I wanted to say for today. And tomorrow I'm at what time? We don't know. But I'll continue on then with quantum information.
Other questions? I have one question. The embedding chi, we asked that is causality preserving always?
Yeah, it has to be, because you look at this example. So you don't want it to happen that if I have a region and I embed it, that I have new causal geodesics between. That's what is meant by causality.
So I mean the factor alpha is defined for chi, which is causality preserving.
Yeah. So the embeddings which are considered are the causality preserving isometric, not just isometric. Because otherwise, it's just you have secretly a propagation like around the back.
Yes.
Also, I heard that on top of this, once consider causality preserving, and that maps Cauchy per surfaces to Cauchy per surfaces. Have you ever heard about that?
I think causality preserving captures the essence of what you want to talk about. You're right. If you have gauge theories, it all becomes more complicated, because you can have Aharonov-Bohm type phases. So if you have a region with a hole, there's no, and then it has these Aharonov-Bohm phases as observables. But if you fill in the hole, so if you embed it into something which doesn't have the hole, then these observables are gone, because there's no Aharonov-Bohm phase you can measure. And so that means the functor maps the observable, like a Wilson loop or something like this, to something which is trivial. Yeah. So it's not it's not algebraically. It's not an, I would say, isometry. It's not injected. These things happen. Yeah. So if you have, you can you can still have global gauge theories, global observables, which kind of disappear. So, but the local ones, the covariance that I stated was only about the local ones.
Other questions? Okay, so if not, we meet tomorrow at 10 with another lecture by 10. Yes. I checked on the yes.
So when should we chat?
We can, now, May to die, we can start.
A little bit.